Evening. I'm spot on weather meteorologist Matthew Euler. Welcome to my latest training video. I know it's been a long while, it feels like, since my last training video. It's been just over a week, but it's amazing how fast the time just flies by. And I want to get back here into the training sessions. And so I'm going to break down this topic of vorticity, and I'm going to break it down into two parts. We're going to do part one this evening, and then hopefully I'll be cutting part two here shortly. But let's go ahead and kick things off. And let's talk about vorticity, which is a very interesting topic when we talk about the field of meteorology. First, let's go ahead and look at the overview. I skipped ahead there. There we go. All right, so first let's talk about the overview of the training. And let me see, let me get my pointer out here. Okay, so we're going to define vorticity in part one of this training video, and then we're going to go into the different types of vorticity. Now, part two, I'm going to delve into vorticity advection itself and the importance of that. If I remember, I will go ahead and maybe show you an example of vorticity charts, the 500 millibar vorticity chart, which is a very important tool used by meteorologists to determine what type of vorticity advection that is coming into an area. So hopefully I remember and I can show you that hand-drawn analysis from when I went to the meteorology school. All right, so let's go into vorticity and let's define it first. All right, so what is vorticity? It's simply a measure of the spin of small air parcels. Now, the faster this air parcel spins, the greater the vorticity. So if we consider the spin of horizontally flowing air about a vertical axis, there are two defined motions in vorticity. We have two types, positive and negative vorticity. With positive vorticity, this is going to occur when a parcel of air spins cyclonically. And in the northern hemisphere, that means the parcel is spinning counterclockwise. And when you have positive vorticity, it's an indicator of upward vertical motion or rising air in the atmosphere. You see over here on the right-hand side, this red air parcel here. And you notice we have the label positive vorticity on top of this red parcel of air. And you notice the counterclockwise or cyclonic flow of the air as it spins. It has positive vorticity. It spins in a counterclockwise or cyclonic manner. And then the other type of vorticity we have is called negative vorticity. And this occurs when a parcel of air spins anticyclonically or clockwise. So you notice these black arrows over here on the right. This is now a blue colored air parcel. But notice the direction of the spin of this air parcel in a clockwise or anticyclonic manner. Whenever you get negative vorticity, you generally get downward vertical motion in the atmosphere or sinking air. So positive vorticity is generally associated with storminess. Negative vorticity is usually associated with fair weather. Additionally, when we talk about vorticity, it is a cumulative effect and is a great indicator of what is happening to the vertical motions within a system in general. Now, vorticity can be defined in the following manner, and we're about to break down all these other types of vorticity, okay? We're going to talk about shear vorticity, curvature vorticity, relative vorticity, planetary vorticity, and then absolute vorticity. Right, so these are what we're about to cover here in vorticity part one training this evening. Shear vorticity plus curvature vorticity generally gives you relative vorticity. When you take relative vorticity and combine it with planetary vorticity, that's what gives you the absolute vorticity. So this is the general mathematical formula for the different types of vorticity. And here are those other vorticity types: shear vorticity, curvature vorticity, relative vorticity, planetary. We can also refer to planetary vorticity as Earth vorticity. And then we have absolute vorticity. Let's first talk about shear vorticity. This is defined as the change caused by this side-by-side speed shear or lateral speed shear, or more simply, a change of speed over a horizontal distance. Now, if we were to examine what occurs in a river, for example, near the center of the river, the water is flowing faster than near the banks. And this change in water speed over the horizontal distance of that river causes, if we were to have a canoe in that river, it would cause that canoe to rotate. Okay? So this is a great analogy. We can use the river. We're going to kind of get into, the different types of vorticity here now. All right, so let me draw this out for you, okay? And hopefully you'll understand this better when I draw it out. All right, so shear vorticity, okay? So let's imagine that these lines here I'm drawing represent the river bank or the edge of the river. What we're saying is if we have a canoe, let's just say we have a canoe right here in the middle of the river. The flow of the water is going to be fastest in the middle of the river. So let's just label the middle of the river here, the water flow, and I'm just going to represent it with the letter F for fastest moving water. Okay? Now, let's say we examine the water speed along the river edge or the river banks. It's going to be slower. The water is going to flow slower. I'm going to represent slower with the letter S along the river bank. So we have faster flowing water in the center of the river, slower moving water on the edges of the river in the riverbank. And we have so I'm not the best artist here, as you can tell, but this right in the center here represents a canoe. So I'll just label this, I'm going to go ahead and spell it out, okay? So this is a canoe in the center of the river where the water speeds are flowing the fastest, okay? All right, so we got our drawing down now, right? All right, so now let's continue to talk about things here. The first bullet here saying that faster water on one side will pull the canoe in that direction, thus creating a spinning canoe. So if we have faster moving water basically on one side of the canoe, it is going to cause that canoe to kind of rotate. So let's just use the second bullet here. Let's say the water on the left side of the canoe is moving faster than on the right side. So let me go ahead and let me see if I can erase this. Let me see if I can erase this here for us. Let's do this. Eraser, and let's go ahead and we'll just erase the slow and the fast speeds here, okay? Now let me go ahead and draw out the riverbank on the other side again. Okay, so this is our riverbank, the other side of the river. Okay, and now we have the canoe here, and what we're saying is if the water on the left side of this canoe, so let's just use some numbers here. Let's say the water on the left side of the canoe is moving along at 10 knots. Okay. Or actually, to make it more simple, let's just say 10 miles per hour. All right, so the water's flowing at 10 miles per hour on the left side of the canoe, to the left of the canoe. And then on the right side of the canoe, the water is at, let's say, 5 miles per hour. Okay? So 5 miles per hour, the water's flowing on the right side of the canoe. On the left side of the canoe, it's flowing at 10 miles per hour. All right, so the back end of this canoe or the boat, if we call it a boat, we can call it a boat. But let's just call it a canoe. The back end of this canoe is going to try to spin forward, pulled by faster waters. The canoe would then be spinning down the river clockwise or anticyclonically. So the big thing here with the speed difference, this is a lateral speed difference right here. This is lateral shear, lateral speed shear, because we have changing speeds within the river, right? From one side of the riverbank to the other side of the riverbank, okay? And so this canoe is going to start rotating basically in a clockwise manner. The back end of this canoe is going to get moved. As this canoe's trying to move forward, the back end is going to spin towards the faster side on the left side there. So this canoe eventually over time is going to be spinning clockwise or like this. All right, it's going to be spinning like this as it goes down this river. Okay. Here's a better diagram, right? Compared to my artistry here. But we are still talking about the scenario here, the lateral speed shear, the shear vorticity. The opposite occurs when the water on the right side is moving faster than that on the left. In that case, the canoe would start spinning counterclockwise or cyclonically. So we look at a river, we look at a canoe, and you know what? We're just kind of comparing the speed of the river, how fast it's flowing. In this example, we have the river flowing at 10 knots to the left of the canoe, and we have the river flowing at 30 knots near the center. Here comes the canoe down the center of the river. Basically, what's going to happen is this canoe is going to start spinning more. In this case, it's more anticyclonic. But it also could spin with faster water or faster river speeds to the left. It could spin the opposite direction counterclockwise. So we are using a river to kind of set the example of shear vorticity. But if we were to use the atmosphere, we'd be talking about air flowing in the upper levels of the atmosphere. Like in it, let's say like, for example, at 500 millibars, 18,000 feet, we would have these different wind speeds going on in the atmosphere, and it would cause air parcels to either spin counterclockwise, positive vorticity, or clockwise, which would be negative vorticity. So, all right, so shear vorticity, applying the concept to the winds. Let's just say the jet stream, we can also use that as a comparison. The strongest flowing wind in the atmosphere is in the jet stream. It acts the same way as that river we just looked at. So left of the strongest winds, or the jet stream axis, the difference in speed shear causes the air parcel to spin cyclonically, imparting positive vorticity. Right of the strongest winds, the shear, or that difference in speed, causes the air parcel to spin anticyclonically, resulting in negative vorticity. So again, we're using winds in the upper atmosphere. We use the river analogy. Just realize again that it depends on where the fastest speeds are located in relation to the parcel. We could substitute this canoe for an air parcel in the atmosphere and compare the winds on both sides of the air parcel, similar to the way we're doing in a river here with a canoe. And basically, left of the strongest winds, again, the difference in speed shear, the air parcel spins cyclonically, and to the right of that strongest wind, the shear causes the air parcel to spin anticyclonically. All right, here's another example with shear vorticity. The greater the change in wind speed, you're going to have the greater the shear. All right, stronger shear is going to yield stronger shear vorticity, which makes a lot of sense. Now, if there's no change in the wind speed over distance, there is going to be no shear. So, for example, if you're right down the center of the jet stream core itself, you won't have any difference in the wind speed. All right, so right down the center of the jet stream core, that would be synonymous with the center of the river, okay, that we just looked at. Let's examine now over here on the right. Let's examine these wind speeds. And let's examine which way the parcel would turn or rotate. So this right here is your jet core, this 50 knots right down the middle. This black dashed line, this is your jet core, the center of the jet stream, all right? So you're not really going to get any shear right here down the center of the jet stream. However, if we're basically going to be, let me draw this out, all right? We basically are looking at westerly winds in this example on the right. So my wind is basically going to be blowing from left to right on your screen. Okay, this is a westerly wind. This is 50 knots, two black darkened triangles, each one of, actually, no, that's not 50 knots of shear. That would be that'd be 100 knots down the center of this thing. But regardless, what we're looking at here is what's the air parcel doing over here and what's the air parcel doing over here. So we have lighter winds to the left of the air parcel, if it's right in here. We have lighter winds, 20 knots over here. Let's just say it's 20 knots, and then we have 50 knots here. So the parcel is going to basically spin cyclonically, okay? And to the right of the center of this axis, we have anticyclonic spinning of the parcel. So you're comparing the wind speeds. This is more than 50 knots right here, and I apologize for the typo here. This is actually 100 knots. When you have two triangles like that on a wind bar, that's 100 knots wind speed. This is 50 knots here. This is 50 knots here. Okay, and then we got, this should be 30 knots of wind here, 30 knots over here. So basically what you're doing is you're comparing, the wind speeds in relation to the left or the right of the air parcel, and determining whether this parcel is going to spin cyclonically, counterclockwise, resulting in positive shear vorticity, or anticyclonically negative shear vorticity. So the differences in wind speeds in the atmosphere really, really matter as far as how air parcels are going to rotate or spin. When we talk about curvature vorticity now, we're going to talk about the spin imparted to an air parcel caused by a change in wind direction. Shear vorticity was caused by a change in wind speed, but curvature vorticity is caused by a change in wind direction. It's caused by the troughs and ridges that we see in the atmosphere. As an air parcel moves into a ridge, it spins more anticyclonically, and just the opposite is true for troughs, with the parcel of air spinning cyclonically. So let's take a look at this. So with curvature vorticity in a ridge, the curvature spin in the air parcel is anticyclonic, and the curvature vorticity becomes more negative. I think I have a diagram. I'm going to show you that here in a moment. A parcel moving through a trough spins more cyclonically because of curvature, increasing its positive curvature vorticity. Faster winds or a smaller radius are going to result in greater curvature vorticity, since the directional change is sharper for faster, speeds. It is easier to drive around a shallow curve slowly than it is to go around a hairpin turn at a high rate of speed. And we've all experienced that in our life, where you see the sign, the hairpin turn sign, when you're getting off an exit off the interstate. You're going to pump the brakes, right? You're not going to keep going 60 to 70 miles per hour around a hairpin, really tightly curved radius coming off the interstate. But if it's more gradual of a curve coming off the interstate, you're not going to feel the effects as drastically, okay? With curvature vorticity, you got to have the curvature. I mean, bottom line, right? You either got to be in a trough or a ridge in the atmosphere to get curvature vorticity. Some areas of the atmosphere have simple straight line wind flow. These are known as inflection points, and these are usually going to be located between basically the transition from a trough to a ridge and inflection point from a ridge to the trough. At inflection points, there's basically zero curvature vorticity. Here is an example of trough and a ridge and the turning of this air parcel, right? So as the air parcel comes into this trough, right here is a trough. Okay, this is a trough. As the air parcel kind of comes through the upper level wind flow here into the trough, it's going to rotate cyclonically or counterclockwise. And this is going to result in positive curvature vorticity. That's what that plus sign indicates, positive curvature vorticity into a trough. As the air parcel comes out of the trough and is working its way from southwest to northeast towards the ridge, this is an inflection point here. You notice how there's no plus or minus in this particular value here, or this circle here, this air parcel. There's no turning of the wind direction. There's no change in wind direction here. We have straight line flow at the inflection point. And then by the time that parcel gets to the top of this ridge, you're going to have maximum anticyclonic turning, and this is going to result in negative curvature vorticity in the ridge. All right, so let me just do a quick rehash here. I'm going to label the trough as a T. I'm going to label the ridge as an R. Now keep in mind, this is above the surface. This is the upper levels of the atmosphere. This could be at 500 millibars with shortwave troughs and ridges. This could be at 300 millibars with longwave troughs and ridges. Bottom line is, in the trough, an air parcel is going to have positive curvature vorticity, rotate cyclonically. This I is going to represent the inflection point right in here. We basically have straight line wind flow, no curvature to that. And then as the parcel moves up to the ridge axis here, it's going to spin more clockwise, anticyclonically, resulting in negative curvature vorticity. So hopefully you get this now. You have to examine where the air parcel is in relation to the trough ridge pattern. And yeah, the inflection points again are going to be right here. They're the transition point between the trough and the ridge. And this is the other inflection point area here, the transition point between the ridge back to the next trough. So there you have it. Now, relative vorticity, what is this? Let's say we combine the shear vorticity. Again, that shear vorticity is caused by differences in wind speed, and the curvature vorticity caused by just basically curved flow into troughs and ridges. So if we take both combined effects of shear and curvature vorticity, take those two and add them together, sum them up, you are going to get relative vorticity. So relative vorticity is basically shear and curvature vorticity combined. And it's going to be the best measure of system strength. It measures an air parcel spin in relation to the Earth. Now, let's examine this chart here over on the right. Okay. Now that we know the relative vorticity is basically the combination of shear vorticity plus curvature vorticity, let's examine now different possibilities. So let's say we have positive shear vorticity and we add positive curvature vorticity. All right. That is going to give us positive relative vorticity. That's pretty much makes sense, right? We have positive shear vorticity and positive curvature vorticity. That means I'm in a trough. I'm going to get positive relative vorticity. That's going to result in rising air motion, upward vertical motion, UVM, and that is going to give me a lot of clouds and most likely some sort of precipitation. On the other hand, let's say now I have negative shear vorticity and I also have negative curvature vorticity. I add those two together, a negative and a negative. I add those two together and I'm getting an overall relative vorticity that's negative. I'm getting downward vertical motion, DVM. Air is sinking. As air sinks, it dries out, it warms, and that results in fair weather. Now, let's say I'm doing an analysis and I notice that we're at an inflection point here. So I have neutral or zero curvature vorticity at an inflection point. And let's say I'm right down the center of a jet stream core. I'm also going to have zero or neutral shear vorticity. So if I have neutral or zero shear vorticity and neutral zero curvature vorticity, that's going to make my relative vorticity also neutral. When I have a neutral vorticity, relative vorticity, that means it does not favor rising or sinking air motion in the atmosphere. Now, what happens when we have positive shear vorticity plus negative curvature vorticity? Well, I really don't know what the relative vorticity is going to be. I don't know if it's going to be positive or negative in this case. And the same thing goes for the last example. Negative shear vorticity plus positive curvature vorticity. I really don't know. Notice the question marks on what that relative vorticity is going to be, whether it's going to be positive or negative. I need to know more information. Now let's examine planetary. Sometimes this is referred to as Earth vorticity. The Earth is rotating, as we all know, and it does have its own form of vorticity because of this rotation. In the Northern Hemisphere, planetary vorticity is always positive because the Earth is spinning counterclockwise or cyclonically. If you were to go directly above the North Pole and see the Earth rotating or spinning, it would be doing so in a counterclockwise or cyclonic manner. So that's why we say the Northern Hemisphere always has, its planetary vorticity is always positive because of this fact. And you can see it right here on the right-hand side graphic. All of the Earth's spin contributes to the parcel spin about its axis, and it's more of a cyclonic or counterclockwise spin over the North Pole there. Now, the amount of planetary or Earth vorticity is going to depend on the latitude. The rate of spin is going to increase from 0 at the equator to a maximum spin rate at the poles. Planetary vorticity is greatest at the poles and 0 at the equator. Let's look at this image here on the right and let's examine it in full detail. At the equator here, we have this cube-looking structure represents the air parcel in this example. So imagine that these boxes or these cube-like structures, they represent an air parcel. So at the equator itself, the Earth's axis of rotation is perpendicular to the parcel's axis. So the Earth's spin does not contribute to a parcel spinning because the axis of rotation of Earth, again, is perpendicular to the parcel's axis. Now let's continue to gain, let's go north here. Let's gain some latitude. So now we're going to go north from the equator and at points in between the poles up here and the equator down here, okay? At the points in between those two areas, the poles and the equator, some of the Earth's spin is going to contribute to the parcel spin. And then by the time we get all the way up here to the North Pole with this air parcel, all of the Earth's spin contributes to the parcel spin. So what does this mean based on latitudes in the Northern Hemisphere? Your planetary vorticity is 0 at the equator. Absolutely 0. Let's just say 45 degrees latitude is here. You are going to get some sort of spin with the air parcel here at 45 degrees latitude, but you're going to have the greatest spin in a cyclonic or positive vorticity manner. This is going to have the greatest positive vorticity up at the polar area, the North Pole area. All right, so for absolute vorticity now, let's talk about absolute. We just talked about planetary or Earth vorticity. Now let's look at absolute. Now absolute vorticity, it represents the total amount of spin that a parcel possesses. Okay. We take shear vorticity, do those changes in the wind speed in the lateral or horizontal direction, and then we add curvature vorticity due to the parcel moving through the ridge and trough, we get relative vorticity. Now what happens if we take the relative vorticity and add it to planetary or Earth vorticity? We get absolute vorticity. That takes into account all the vorticity types. So shear curvature gives you relative, and then relative plus planetary or Earth vorticity, absolute vorticity is the results. It's the total vorticity. All right, so that wraps things up for part 1 of my vorticity training lecture. We are going to get into the vorticity advection types in my next vorticity training video. We got 2 parts of this thing. I wanted to basically break it up. It's, pretty beefy topic here, but we will get into vorticity advection. We will get into, what type of charts we look at for vorticity advection. We'll talk about what's known as positive vorticity advection. We'll talk about the results of positive vorticity advection on upward and the upward vertical motion aspect. We'll talk about negative vorticity advection in the next training video. And then we'll look at, how do you determine whether it's negative or positive vorticity advection. Negative vorticity advection, we'll talk about the type of weather you get with it. We'll talk about neutral vorticity advection in the next video. And then we'll also talk about vorticity advection in association with the jet stream maximums, curved and straight line flow, and we'll talk about that a little bit more. So that's all I got for now, everybody. I hope you enjoyed the presentation. In tonight's video, in summary, we covered what vorticity is, and that basically means what it is a measure of the spin of small air parcels. The faster the air parcels spin, the greater the vorticity. When they spin counterclockwise, indicates positive vorticity. When an air parcel spins clockwise, it indicates negative vorticity. Why does this matter to our weather? Well, when an air parcel spins counterclockwise or cyclonically, when positive vorticity occurs, we generally get upward vertical motion, rising air, clouds, and precipitation. When we get negative vorticity advection, we get fair weather because the air is downward vertical motion. We have downward vertical motion directed air and sinking air motion. We looked at the various types of vorticity. The cumulative effect of the vorticity yields absolute vorticity. And then we looked at the specific different types of vorticity. Remember, shear vorticity is just the change caused by lateral speed shear, wind speed changes over a horizontal distance. We used the river analogy. We also looked at, after the river analogy, we then showed you the canoe in the water, and it's either going to spin clockwise or counterclockwise, cyclonically or anticyclonically. And then we looked at, applying that shear vorticity to the real atmosphere with the jet stream, kind of showing you some examples here. And then we looked at curvature vorticity, examined that into troughs and ridges. Remember, curvature vorticity is negative into ridges and it's positive into troughs. And the point in between the ridge and trough, it has straight line winds, so no curvature. That's the inflection point, which we showed right here. And then we examined relative vorticity, which is a combination of the shear and curvature vorticity. We examined planetary earth vorticity as well. And the total of all of vorticity gives you absolute vorticity. And that is all I got for now, everybody. I'm planning on covering maybe 3 or 4 more videos for the training series this summer. And then we'll start examining some of the operational charts, weather charts, as we get into September, into the fall season. And so very excited to continue. I really appreciate everyone's subscription to Spot on Weather YouTube channel. Until next time, everybody, take care and God bless.